let's recall that the sine transform maps this region from minus pi half to pi half onto this region. And since the function is conformal, the derivative exists at every point, and the derivative is different from zero, we also have an inverse function because it's conformal in this entire region, this square. Therefore we have an inverse sine inverse which goes from, has this region as definition and this as value set. Let's have this in mind in the next example, because in this example we are going to consider the case when we have a boundary condition t equal to some constant, which in this case is equal to 0 on this part, and on this green part the temperature is constant equal to 20. In between we just have this insulating boundary condition. That means that the normal derivative should be equal to 0 through this boundary. But just keep in mind the sine transform. It has this property, and what we should like to do is to use this inverse sine transform in order to transfer our problem from this region to this region, because in this region it's very simple for us to find the solution of the temperature problem. So using the inverse sine transform we may be able to do this. So what we have here is that we have the real problem where we are going to find the solution looks like this, and taking the inverse sine transform, which is called f of z, we may transform this or map this region onto this rectangular region, and the temperature condition, boundary conditions are also mapped. So we are mapping this line onto this line and this green line onto this green line. But this is a very trivial problem to solve, because this problem is only dependent of the x direction, or as usually we call this coordinate system the u-v coordinate system, in order not to confuse with the coordinate system of our original problem, which is the xy coordinate system. We know the temperature in the case when we write, we let the horizontal direction be the x direction, then the temperature is some constant a multiplied with x plus b. In this case we have replaced the x-axis with the u-axis, so we must also replace x by u. And in this case it's very trivial to find the solution. The values of a and b are found by inserting the u value minus pi half into this expression, and we know that the temperature is equal to 0, so it's really on the for this u value. And we also know that when u is equal to pi half, the temperature should be equal to 20. So using these two boundary conditions, we are able to find a and b similarly as before, and we obtain that a is just equal to 20 over pi and b is equal to 10. So we obtain this expression for the temperature in this domain. And similarly as before, this implies that the complex potential can be written in this way, where W is just equal to U plus IV. So, well, the temperature, the harmonic part, the real part of this complex potential is of course this temperature T star. Exactly as we had done before, instead of using no set, we write f of set. So we are replacing this value of the complex potential with this W f of set. Doing this, we obtain a new complex potential in terms of set, which is the complex potential of this problem. So we know that f of set is just equal to W from this expression, and W is equal to the inverse of sine set. So we replace f of set by the inverse of sine set, and then we have the complex potential, and finally the temperature. We just have to in order to find the temperature, we just have to use the real part of this complex potential, and the real part of this is just the real part of the complex potential. And well, we are maybe able to reduce this problem, but in fact this is the expression, the simplest expression for the solution of our problem.